Hi, I'm Gilles Callebaut, and I will present our work on sub-GHz massive MIMO for low-power wide area networks. This work was a joint effort by Lund University from Sweden and KU Leuven from Belgium. While many other researchers primarily focus on broadband, high throughput and low latency communication, in this work we look actually, and quite literally, to the other side of the spectrum. Here we investigate deploying massive MIMO for IoT and machine-type communication. Furthermore, others have used channel models such as Rayleigh fading models, while here we have collected real-world channels in an outdoor scenario. We have used two array configuration, the uniform linear array and uniform rectangular array, designed to operate in the 868 MHz band. By going sub-gigahertz, we are actually trying to answer the age-old question, does size matters? Before delving into that question, let me introduce our team, because credit where credit is due. Sarah Gunnarsson at the left is the guru of the NI framework used in the massive MIMO testbed. It's the National Instruments software running on the testbed, which is doing all the massive MIMO stuff. Andrea at the back was our testbed operator and guru of the testbed herself. Anders, Lisbeth, and Frederick helped us to analyze the results and explain and pinpoint phenomena which we could sometimes not explain or dare explain. And there is me, Gilles Callebaut. Our research was funded by the ORCA project. In this project, we made a video which encompasses what we did and why. The following video serves as an introduction of this experiment. Note that it was designed for a broader public. I will go into more detail after the video. We also cut some parts to fit in a 50-minute window of the conference presentation. I would also like to take the opportunity to show the difference between simulations and real-world experiments. So what are the things we bumped into and what are the preparations we have taken prior to the experimentation phase? First, we started with designing the holders for our antenna array at the base station. We wanted a flexible design which was easily moved and configured. Every holder consists of two patch antennas and is made out of plexiglass. The holders are fixed in place by mounting fin connectors between two holders. These connectors you can see at the right side of the slide. The holders have notches on all edges which allow for connecting holders in different topologies. In these experiments, we are using the license-free SRD 860 band, also commonly known as the 868 MHz band. In this band, a couple of restrictions must be taken into account in order to comply to the regulations. The 868 band is divided in different subbands, each having its own restrictions. The first restriction is the maximum allowed transmit power. It is defined as the effective isotropic radiated power, so you will need to subtract the gain of your antenna from the transmit power. In IoT networks, the high power band is mostly reserved for gateways, while the end devices use 14 dBm bands as they are often battery powered and thus are power constrained. Secondly, the devices are required to sleep a period of time after transmitting a message. Another reason gateways are often deployed in the high power band is because they also allow a higher duty cycle in that band, so 10%, while the nodes operate in the 0.1 or 1% band. Lastly, the occupied bandwidth needs to be restricted to a maximum of 200 kHz. The NI framework, which we were using in the testbed, developed by National Instruments, has by default a 20 MHz band. So to respect the maximum bandwidth of 200 kHz, we only use 12 subcarriers from the OFDM signal to get a bandwidth of 180 kHz, which is of course smaller than the allowed bandwidth of 200 kHz. We also measured this at the port, so we indeed comply to the regulations. We used the NI LTE default. We adapted the NI LTE default frame structure to also comply to the duty cycle restrictions. So the default frame structure, there you have a radio frame of 10 milliseconds, which is divided by divided in 10 subframes, each having 2 slots. So the first subframe 0, is a bit different than the other because they also have a specific slot where there is a sync, and the sync is used for the synchronizing the user equipment or the node to the base station, and then the rest of the slots are actually divided as this. So you have an uplink pilot, so from the node to the base station you have some uplink data, then you have an empty band, so it's a guard band, so you can switch from uplink to downlink. Then the base station can send a downlink pilot and downlink data, and this is repeated for slot 0 and slot 1 for subframes 1 to 9. So we changed it so we could actually have or comply to the duty cycle restrictions. So we only use slot 0 and subframe 0, and we use one uplink pilot and two times uplink data. The uplink pilot is used to get the channel, so collect the channel, and we have the uplink data to collect the signal to noise ratio. As you can see, we do not longer have the synchronization, so we have to synchronize the base station and the node in another way. To do this, we used rubidium clocks. We put one rubidium clock to the base station, another one to the node. The rubidium clocks are each synchronized to each other. To do so, we had to put them together for 8 hours so they could synchronize themselves. One small note is that the rubidium clocks had to be powered the whole time, and when they lose power, they lose sync. So we had to let them stay powered on. At the node side, we had the antenna holder, which holds the antenna 1.5 meters above the ground. We have the UPS powering the rubidium clock, which allows it to be easily moved without a cable. We have a LiPo battery with a DC-DC converter, which is connected or powering the USRP. So that's a software-defined radio from National Instruments. And then we have the laptop hosting the NI framework or the device side with a PCI Express slot, which is connected to the USRP. As you could see here, we had to have a cargo bike to easily move. So we had a lot of equipment at the user equipment side. So there were a lot of preparations done to be able to do the experiments, but even then at the mercy of weather. So actually when we wanted to start the experiment, it started to rain, which is quite commonly in Belgium. And besides that, we also had Corona. So we intended to start the measurements in March. So as you could see here, this is the balcony where the base station was put, and you can see the field. So we have actually we have a line of sight to the base station. But then Corona hit, and we had to postpone the measurements. And when we actually could start the measurements, this happened. So we do no longer have the line of sight as we first intended. So these are the discrete points of the measurements, and as you could see, what we intended, so for the red point, we intended that it was a line of sight, but now it's no longer a line of sight. These are the results of the measurements we have done. So first we looked at the channel hardening, which means that if we have more antennas at the base station, the variance of the channel gain decreases. So this we could see as well here. So we have the difference between the channel gain with respect to the time for one antenna and for 32 antennas. And as you could see here is that the variance decreases when having more antennas, so 32 opposed to 1. So actually our fading multi-antenna channel behaves more like an deterministic scalar channel. So we could rely actually on the average gain and do not need to worry much about fading. What we also noticed was the large scale fading over the antennas. As you could see in the graph, we have in the x-axis the antenna index and in the y-axis the channel gain. Here we plotted the channel gain for the two configurations at 2 points. First we have a line of sight point close to the base station, and then we have a non-line of sight point further away from the base station, 100 meters to be precise. We see the effect of large-scale fading over the different antennas, and this is certainly visible when looking at the URA for the non-line of sight point. This shows the benefits of having multiple antennas. While some antennas are blocked or experience some shadowing, other antennas contribute much more compared to those. This is certainly visible when you're in non-line of sight. You could also observe that the variance decreases from going from non-line of sight to line of sight. So what we mean by variance is the difference between the channel gain per antenna varies between these antennas. So from a line of sight you have, for instance, for the URA 2.1 dB, while in the non-line of sight you already have 3.84 dB. So you get more variance when going non-line of sight. What we can also observe here is that you receive more power or more we have a higher gain for the URA than for the ULA in both scenarios. While you have more power for the URA than for the ULA, this does not hold for the correlation. So if we've computed the correlation with respect to the number of antennas by using the correlation coefficient, and we also made the graphs a bit smoother by windowing over the antennas. So for instance, if we have two antennas here on the x-axis, we actually average over two consecutive antennas. So we window like this over the antenna configuration. What we could see here is that both ULA and URA have the same or decorrelation when going towards 6 antennas. But as you could see, from 7 antennas, the URA flattens a bit and doesn't decorrelate as much as the ULA, meaning that stacking for the URA, stacking the ULAs of 8 antennas do not contribute to the decorrelation of the channels as much. To conclude, the increased received gain of using multiple antennas allows IoT nodes to lower their transmit power. Due to smaller variations in the channel, the fading margin used at the node sites can be reduced or even omitted. So that also affects the transmit power. As we get a more reliable flat channel, the energy required to do retransmissions due to fading and other energy consuming scheduling algorithms can be relaxed, lowering the overall energy consumption of the node. Visit our website drumco.be/massive MIMO to get your hands on the collected channels. We welcome everyone to work with our measurement data. For any questions, do not hesitate to contact me. Thank you.